For 90 years, scientists thought they understood Platybelodon, a swamp dweller, a mud scooper, an evolutionary punchline with a face that looked like someone had welded a shovel to an elephant's chin. The kind of creature you point at in a museum and say, well, that clearly didn't work out. They were completely wrong. This wasn't nature's rough draft. This was one of evolution's most sophisticated experiments, a living scythe that dominated an entire continent for 5 million years. And here's the part that will change how you look at every elephant you ever see again. That ridiculous, impossible face. It helped create the elegant trunk that modern elephants use today. To understand how something this absurd conquered Eurasia, we need to go back to a time when elephants were still figuring out what an elephant should even look like. The Middle Miocene, 15 to 10 million years ago. If you're looking for the golden age of elephant experimentation, this was it. Picture a world warmer than today but cooling fast. Forests that had dominated for millions of years were retreating, and in their place, something new was spreading: grasslands. Endless seas of tough, silica-filled grass stretching from horizon to horizon. For the proboscideans, the elephant family, this was both an opportunity and a crisis. See, forest-dwelling elephants had it easy. Soft leaves, tender shoots, fruit if you were lucky, but grass fights back. It's loaded with microscopic silica particles that wear down teeth like sandpaper. Eating grass for a living requires specialized equipment, so evolution did what it does best. It experimented. Dozens of elephant lineages tried different solutions, different tooth patterns, different jaw structures, different ways of grabbing food. More elephant species walked the earth during the Miocene than at any other time in history. Most of those experiments failed. One of them, the most extreme of all, would change everything, just not in the way you'd expect. Let's talk about what Platybelodon actually looked like, because the reality is even stranger than the museum reconstruction suggests. Start with the basics. Total length, 4.5 to 6 meters. That's 15 to 20 feet, roughly the length of a large SUV towing a small trailer. Shoulder height, 2.2 to 2.8 meters, or about 7 to 9 feet. That's roughly the same as a female Asian elephant. Weight, somewhere between 2 and 4 tons, depending on the individual, so anywhere from a pickup truck to a small dump truck. But here's where it gets weird. The mandible, the lower jaw. In most animals, the lower jaw is just there, functional, forgettable. In Platybelodon, the lower jaw extended forward over 1 meter. That's more than 3 feet, longer than a baseball bat. And at the end of that jaw, 2 flattened tusks had fused together into a broad, curved surface, about 30 to 45 centimeters wide. Roughly the size of a large laptop, but made of solid bone and enamel, with edges worn sharp from use. Males were larger than females, with more pronounced mandibles and curved upper tusks that pointed downward, possibly for combat, possibly for display. Because apparently having a face like a construction vehicle wasn't enough, and the trunk? Scientists used to think Platybelodon had a short, stubby trunk, more like a muscular upper lip. But recent analysis of the skull's nasal region tells a different story. That trunk was functional, capable of gripping, not as long as a modern elephant's, but far more developed than anyone assumed. Let that sink in. Evolution looked at a perfectly functional elephant face and said, what if we stretched the lower jaw until it was longer than a human leg? And then it worked, for 5 million years. So we've established how strange this animal looked, but here's where it gets interesting. For 90 years, we had no idea what it actually did with that face. The name says it all. Shovel-tusker. That's what everyone called Platybelodon from the 1930s onward. The assumption seemed obvious, that flat, broad mandible must work like a shovel. The animal must have lived in swamps, scooping up mud and aquatic plants, filtering out the good stuff like some kind of prehistoric dredging machine. It made sense. It fit the shape. It became textbook fact for nearly a century. There was just one problem. When scientists finally examined Platybelodon teeth under an electron microscope, they didn't find what they expected. If you spend your life scooping through mud and water, your teeth get polished smooth. Fine sediment and liquid create a gentle, even wear pattern. But Platybelodon's teeth? They were covered in deep scratches, pits, heavy abrasion marks. This wasn't the wear pattern of a mud scooper. This was the signature of an animal grinding through tough, hard material, bark, woody stems, grass loaded with silica. Then came the bombshell. In 2023, researchers used finite element analysis, the same computer modeling technology used to stress test bridges and aircraft, to simulate how Platybelodon's skull would handle different forces. The results were definitive. Vertical scooping motion, the mandible would crack. The skull wasn't built to handle upward force at the end of that long lever arm, but horizontal force, sideways sweeping motion. The skull was perfectly optimized. Every bone, every angle, every structural reinforcement was designed for one thing: cutting laterally. Platybelodon wasn't a shovel, it was a scythe. Here's how it actually worked. The trunk, more capable than anyone realized, would wrap around a clump of grass or a branch, hold it tight. Then the animal would sweep its massive head sideways, dragging that sharp mandible edge through the vegetation like a blade. The combination of trunk grip and jaw sweep created a shearing action powerful enough to slice through stems as thick as your wrist. Not scooping, harvesting. A biological reaping machine backed by 4 tons of determined herbivore. And here's why this matters beyond just correcting an old mistake. Platybelodon represents a critical moment in elephant evolution. In earlier proboscideans, the jaw did most of the work. The trunk was secondary, a helper. But in Platybelodon, the trunk had to grip, had to manipulate, had to become an essential partner in feeding. This was the training ground. The evolutionary pressure that forced trunks to develop precision. Modern elephants completed the transition. Trunk does everything, jaw reduced to nothing special. But that process started here, with creatures that looked like evolution's rough draft, but were actually running a very sophisticated experiment. So Platybelodon wasn't a clumsy mud scooper. It was a precision cutting machine that dominated from Russia to China for 5 million years. But even the most sophisticated machine has a breaking point, and we have the fossils to prove it. Tungur Formation, Inner Mongolia. 13 million years ago, this was savanna country. River systems cutting through grassland, seasonal floods alternating with brutal dry spells. The kind of environment where survival meant knowing where the water was. In 1930, a team from the American Museum of Natural History found what they called the Platybelodon Quarry, a concentrated deposit of bones. What they uncovered tells a story no one wanted to hear. 16 individuals, at minimum. Mostly adults, multiple age groups represented. The remains weren't scattered randomly. They were concentrated, overlapping, as if these animals had died together in one place. Family groups, herds. And then there was the pregnant female. Fetal bones still visible in the pelvic region. A mother who never gave birth. The interpretation is grim but straightforward. Drought. These herds had congregated around shrinking water sources as the dry season stretched on. Competition for dwindling resources, starvation, dehydration, disease spreading through stressed, weakened populations. They died at the waterhole, one after another, until the rains finally came. Not to save them, but to bury them. Flash floods sealed the remains in sediment, preserving them for 13 million years. Platybelodon wasn't alone in this world, of course. The Tungur ecosystem included Kubanosaurus, giant pigs with a single horn on their foreheads like something out of a fever dream. Amphition, the bear dogs, apex predators the size of polar bears. Machairodus, early saber-toothed cats that would have circled any weakened herd looking for stragglers. So basically, imagine dying of thirst, surrounded by your entire extended family, while saber-tooths wait for someone to collapse. Then a flash flood buries everyone together for 13 million years. Not exactly a peaceful ending, but the Tungur site isn't just a graveyard, it's a warning. because what killed those individuals in a single brutal season would eventually kill the entire species over millions of years. The late Miocene wasn't kind to specialists. Global temperatures kept dropping. Rainfall patterns shifted. The grasslands that Platybelodon had learned to exploit kept spreading, but they were changing too, becoming tougher. More dominated by C4 grasses, the kind packed with even more silica, even more abrasion. Here's the cruel irony. Isotope analysis of Platybelodon teeth shows they were pioneers. They had already shifted from forest browsing to grassland grazing ahead of many other elephants. They were winning the adaptation race, but the finish line moved. The scythe mechanism needed material it could cut, stems with enough structure to shear cleanly. As grasses became tougher and more fibrous, the cutting edge became less effective. You can't slice through something that just bends and springs back. And then came the competition. Around 10 to 8 million years ago, new elephant designs appeared. Tetralophodon, the ancestors of modern elephantidae. Their innovation was elegant in its simplicity. Forget the heavy mandible entirely. Instead, develop a trunk that could do everything: grab, strip, manipulate. Paired with teeth specialized purely for grinding, lighter heads, more flexible feeding strategies, less energy spent hauling around a meter of bone jutting from your face, a better elephant. The trunk that Platybelodon had helped train became so capable that the jaw was no longer necessary. Its greatest contribution to elephant evolution made it obsolete. Sometime around 10 million years ago, the last Platybelodon died. We don't know where. We don't know how. Maybe the last of a shrinking herd, starving as the grasslands grew too harsh even for a scythe. Maybe taken by a saber-tooth, too slow to flee with that massive head. 5 million years of continental dominance. Generations beyond counting. From the Caucasus to Mongolia, they had walked the grasslands like nothing else before or since. An entire lineage of creatures that had solved the problem of survival in ways no other animal had tried, or would ever try again. Gone. Not a single descendant, not a single continuation of that experiment, just bones in the sediment and scratches on fossil teeth that took us 90 years to read correctly. But here's what they left behind: the trunk. The blueprint they helped write didn't die with them. It was inherited by the next generation of elephants, refined, tested against new challenges, perfected over millions of years into the 40,000 muscle marvel that modern elephants use to pluck a single blade of grass or lift a fallen tree. Every elephant alive today carries an echo of Platybelodon's experiment: the precision grip, the manipulation capability, the partnership between trunk and brain that makes elephants what they are. Platybelodon wasn't a failure. It was a teacher, and the lesson it taught is still walking the earth. So the next time you watch an elephant wrap its trunk around a branch, that precision, that flexibility, that impossible grace, remember where it came from: trained in the Miocene, by creatures with faces only evolution could love. Platybelodon wasn't a mistake. It wasn't a dead end. It was a necessary experiment, the kind that looks like failure until you see what comes after. And like all the best experiments, it changed everything. Even the ones that don't survive can reshape the future. Thanks for watching, and until next time.